Hi dear students. In last class we learned Planck's quantum theory. In that Planck's quantum theory we learned electrons from ground state absorbs energy and it gets excited to next energy levels, and from excited states it falls back. While it is falling back to its ground state, it releases some amount of energy, whatever the energy it gained previously. That released energy is emitted in the form of radiation. That radiation has a certain wavelength and frequency. Here, hydrogen spectrum explains the different spectrum formed by the electron falling from the excited state to ground state. And in today's class, we are going to learn few calculations on these spectrum, especially hydrogen spectrum. Once you check the calculation given on the board, the first emission line of hydrogen atomic spectrum in Balmer series with respect to the Rydberg constant R. See here, first emission line. Here you have to understood first emission line of hydrogen atomic spectrum in the Balmer series. See here, instead of giving the values directly, they given some hints here. That is, first emission line, hydrogen atomic spectrum and Balmer series. See here, once we will recall that one. In case of Balmer series, 1, 2, 3, 4, 5 and so on. These are different shells. If electron falls from certain energy level to second energy level, means certain shell to second shell. This is n is equal to 2. See here, if electron falls from certain energy level to second energy level, then it comes under Balmer series and it gives visible region. See here, this is the first possible emission line, and next line is from next level to second, means n is equal to 3, n is equal to 4, n is equal to 5 and so on. First line possible from third shell to second shell, second line fourth shell to second shell, third line from fifth shell to second shell, means here first emission line is from third shell to second shell. And here he given Balmer series, that's why I am considering up to n2. Here, see here, in hydrogen spectrum, to calculate wave number, there is a formula with respect to Rydberg constant R, that is nu bar is equal to R 1 by n1 square minus 1 by n2 square. Here n1 is nothing but this is equal to n1, and see here first emission line in the sense third shell to second shell, then it becomes n2. Now we have to substitute the values, and I am not going to substitute the value of Rydberg constant here because they are asking with respect to R value, R, that is equal to R 1 by n1 square, in the sense what is n1 here? 2. 2 square minus what is n2 here? 3. 1 by 3 square. See here, after simplifying this one, here we will get R 1 by 4 minus 1 by 9. After simplifying these things, here we will get 5R by 36. 5R by 36. They are asking with respect to Rydberg constant, no? That's why without substituting the value of Rydberg constant, I just written R as R. Now check the options given here. They given in centimeters, per centimeters. First one is the correct option according to the calculation. Once again check it. To find out first emission line of Balmer series, first you have to know few things. That is, Balmer series in the sense the electron will fall into second shell. First emission line in the sense from third shell to second shell. Here in Balmer series, N2, N is equal to 2 is N1, and for first emission line, N2 is equal to 3. For second emission line, N2 is equal to 4, and for third emission line, N2 is equal to 5. We will discuss these things under hydrogen spectrum once again in detail. Now we are focusing mainly on the questions given in mains and advanced. Note down please. A very good question is there on board. Why I am telling this is a very good question, Here they gave very good hints to find out the answer. See here, in a hydrogen atom, the transition takes place from L to K shell. L to K shell, that is first hint. They gave the value of Rydberg constant as 1.08 into 10 to the power of 7 per meter. They are asking the wavelength of the light emitted is nearly in the sense approximately, which one is the correct. See here first you have to understand, if transition takes place from L to K shell, then what are the values of N1 and N2? See here, first shell, second shell, third shell, fourth shell no need to write because we want only L and K shell. K shell, L shell, M. KLM. Okay. See here, from L shell to K shell, L shell to K shell in the sense, what is the N value of K? 1. For L shell, N value is equal to 2. For M, N is equal to 3. If transition takes place from L to K shell in the sense, L to K shell, N1 value is equal to 1 and N2 value is equal to 2. It is falling from second shell to first shell. It is nothing but Lyman series. In hydrogen spectrum, we already learned that one. When it is falling in first shell, Lyman series. In second shell, Balmer series. Third shell, Pachan series. Fourth shell, bracket series. Fifth shell, Fund series. From sixth shell, it is Humphrey series. We learned all these different series. Now see here, this is L to K shell in the sense Lyman series, where N1 value is equal to 1, N2 value is equal to 2. It gives ultraviolet radiation, and see here, okay, that is secondary. Now, what they are asking wavelength. We know that nu bar is equal to Rydberg constant or 1 by N1 square minus 1 by N2 square. And here we know that nu bar is nothing but 1 by lambda. Reciprocal of wavelength is nothing but wave number. Now here we can write it as 1 by lambda is equal to, nu bar is equal to 1 by lambda is equal to, what is R value here? 1.08 into 10 to the power of 7. And here what are the values of N1 and N2? 1 by N1 square in the sense 1 square minus N2 is 2, 1 by 2 square. 1 by 1 square in the sense it is equal to 1. 1 by 2 square in the sense 1 by 4. 1 minus 1 by 4, it is nothing but 3 by 4. Now see here, 1 by lambda is equal to Rydberg constant value 1.08 into 10 to the power of 7, and here we got it as 3 by 4. 3 by 4. And see here, 4 ones, 0.42s are 8 and 4 sevens are 28. Now see here, now multiply 0.27 with 3, you will get 0.81. 0.81 into 10 to the power of 7. What is this? This is nothing but 1 by lambda. But actually we want wavelength. We want wavelength in the sense we have to reverse the value. We have to reverse the value in the sense, therefore I am writing wavelength lambda is equal to, we will reverse this one, then we will get 1 by 0.81 into 10 to the power of this 7 becomes minus 7 because we are taking reverse. See here 1 by lambda becomes lambda, these values becomes ulta, okay. See here they are asking nearest value, that's why I am taking it as 0.8, 0.8. See here if we simplify 1 by 0.8 we will get 1s, and here we will get 1.250, 1.250. See here therefore lambda is equal to 1.250 into 10 to the power of minus 7 per meter. See here in the given options answer is not there in terms of per meters, it is there in the form of angstroms. That's why I like to convert this one into angstroms. Therefore I will convert the values into 10 powers, then we will get 1250 into 10 to the power of minus 10 per meter. 10 to the power of minus 10 in the sense it is nothing but 1 angstrom. Therefore it is equal to 1250 angstrom. We calculated in terms of angstrom. Let us check the values. Okay, second one is 1250 angstrom. Our answer is 1250 angstrom. Once again check it. They given one hint, that is transition from L shell to K shell. L shell to K shell in the sense from second shell to first shell. Then N1 becomes 1, N2 becomes 2. By using the formula, that is wave number is equal to R into 1 by N1 square minus 1 by N2 square, we got the value, that is 0.81 into 10 to the power of 7. But to find out wavelength we converted that one. Then finally we got 1250 into 10 to the power of minus 10 per meter, and we are converting that one into angstrom. Let's move to one more calculation. In the next calculation we are going to learn one new formula to find out total spectral lines possible and visible lines respectively during electronic transition from 6th energy level to ground level in hydrogen atom. See here what they are asking here, they are asking total spectral lines possible and also what are the visible lines, how many visible lines are possible in that one. See here there is a formula to find out total spectral lines. Total spectral lines is equal to N2 minus N1, N2 minus 1 plus 1 by 2. See here 6th energy level to ground level. 6th energy level to ground level in the sense, 6th energy level to ground level in the sense, 6th energy is N2 and ground level is N1. Therefore it is equal to 6 minus 1 plus 1 by 2, that is equal to 5 into 6 by 2, that is equal to 30. 5 6 are 30 by 2. Then the number of total spectral lines is equal to 15. There are 15 lines possible when a transition takes place from 6th energy level to ground level. Okay, and they are asking one more thing, that is how many visible lines are possible. See here 6th energy level to 2nd energy level. In between how many are there? 6th one, 5th one, 4th one, 3rd one. Okay, see here 6th one to 2nd one, 5th one to 2nd one, 4th one to 2nd one, and 3rd one to 2nd one. How many lines are possible? 1, 2, 3, 4. 4 lines are possible in visible region. Why I written to here? Because the second one is Balmer series. Balmer series represents visible region. Okay, there are 4 visible and total lines are 15. Out of 15, 4 are visible ones. Visible lines is equal to 4. That's it. Please note down that one and we will move to next one. In the next calculation, we are going to find out the ratio between 2 different series. Okay, we will check that one. The ratio of wavelength for second line of Balmer series and first line of Lyman series of hydrogen atom. We will see that one. N1 value of Balmer series is 2 and N2 value, see here they are asking second line of Balmer series. Second line of Balmer series in the sense N2 value becomes 4 because the first line is 3 to 2 and second line is 4 to 2. And see here, nu bar is equal to 1 by lambda, that is equal to R 1 by N1 square minus 1 by N2 square. See here, what is the value of N1 here? 2. 2 square minus 1 by 4 square. That is equal to R 1 by 4 minus 1 by 16. That is equal to R 3 by 16. R 3 by 16, or you can write it as 3R by 16. Anything will be fine. 3R by 16. Let us check in case of Lyman series. In case of Lyman series, they are asking first line of Lyman series. First line of Lyman series in the sense N1 value for Lyman series 1 and first line in the sense N2 becomes 2. Therefore here nu bar is equal to 1 by lambda, that is equal to R 1 by, directly I am writing the values because already I wrote formula here. See here, 1 square minus 1 by 2 square, that is equal to R 1 minus 1 by 4, that is equal to 1 minus 1 by 4 in the sense 3 by 4. 3 by 4 in the sense we can write it as 3R by 4. Now see here, we have 1 by lambda value for second line of Balmer series as 3R by 16 and 1 by wavelength of first line of Lyman series is 3R by 4. See here, let us check the ratio here. If we take the ratio, just for understanding I am writing here it as B in the sense Balmer series, that is equal to 3R by 16 and 1 by lambda L in the sense Lyman series, that is 3R by 4. They are asking the ratio of wavelength for second line of Balmer to first line of Lyman series. That's why here that is equal to 3R by 4 into 16 by 3R get cancelled, 4 ones, 4 fours are 16, that is equal to 4. The ratio, here I am writing the answer, I will write here, therefore lambda B is to and lambda B by lambda L is equal to 4. Option D is the correct answer. Please follow our channel MrChemistry for regular updates regarding IIT and NEET. Thank you all of you.